So in this video, we're going to look at some more simple harmonic motion. In this particular problem, we're going to take a spring and we're going to pull it downward, and we're going to see what happens when it bounces up and down simple harmonic motion. So first, let's decide which way is positive. Now, since I'm pulling it downward, that's the direction I'm pulling it in initially. I'm going to call downward positive. I know that seems weird, but let's just kind of go with it. Okay, so I'm going to pull it downward, and let's look at the velocities and accelerations. Okay, so this is going to be the graph that's going to result from doing this. So when I pull it down, right when I let it go, it's not going to have any velocity. And notice that it picks up velocity, it speeds up on the way up, but the acceleration is decreasing. So it's speeding up, but the acceleration isn't as much as it is right at the beginning. So that's one of the reasons why this is not, why we can't use the kinematic equations from the beginning of the school year, because acceleration changes. On the way towards the top, when it gets to the very, very top here, the velocity is going to be 0. And the acceleration increases to a maximum amount pointing back towards the middle. So what makes this simple harmonic motion is the fact that the acceleration always points back towards the middle. Then when we get up to the very, very top here, then it accelerates back towards the middle. It picks up speed. These velocities are increasing. And then when it gets back down towards the bottom, the velocities decrease with accelerations pointing back towards the middle. Again, the entire time, notice the acceleration on the way down, on the way up, and back down towards the middle. The acceleration is always pointed towards the middle. All right. Okay. So notice where the position is at its maximum and minimum. All right. So right up here, this says that equilibrium position in this example is set at 1 meter. So right there is the equilibrium position. That's where the acceleration is 0 and the velocity is at its maximum, is here at the 1 meter position. And where the acceleration is its greatest and the velocity is 0 is here at 3 meters and down over here at -1 meter. So the maximum displacement is at 3 meters and -1 meters, okay, whereas the equilibrium is right there at 1. Okay, I think actually that should say the maximum position is at 3 and -1 meters. I need to change that. It's actually the displacement, notice, from here to down here is going to be -2, and from there to up, oh, actually +2 from there to there, and -2 from there to there, since we're calling upward negative. Okay, so we have to figure out all of these things, where these are maximum and minimum: velocity, acceleration, kinetic energy, potential energy, and total energy. So which variables can we determine from just this graph? So we can figure out the amplitude. So again, the equilibrium point right here is at 1 meter. We're pulling it downward first at -1, so the amplitude is 2 meters in this direction from 1 to -1, and then from 1 to 3 is also 2 meters. Okay, so the amplitude we can figure out as being 2 meters. The period, as it says, it's probably easier to determine the period as a time between consecutive similar amplitudes. So at the 3 meter position, the time is 0.28 seconds. Okay, and then when it comes back to the 3 meter position, it's 0.614. So the period, therefore, is a difference in those two, or 0.334 seconds. So we figured out the amplitude, we figured out the period. It's given to us that this is a 1 kilogram mass. So here are all the things we're expected to be able to do. All right, be able to figure out the frequency, angular frequency, spring constant, position, acceleration, force, elastic potential, energy, total energy, kinetic energy, velocity, and linear momentum. In addition, we're expected to be able to graph all of these things with respect to time, then graph all of these things with respect to position. So a lot of stuff that we're going to have to do. All right. So again, we're given the mass and the the mass and the amplitude. We figured that out from and the period from that graph. So one of the things we can use is we can plug into this equation to figure out the frequency. So the frequency is 1 over the period, or 1 over 0.334 seconds, and it turns out to be 3 hertz. Okay. We also know one of the other things we can figure out is the angular frequency. Okay, so the angular frequency is 2 pi f. Remember, we can get that from the equation off our equation sheet. There's several ways we can get that equation, but if we look at this part of the equation sheet before the t, before the t in this parentheses, 2 pi f is the angular frequency. To figure out the angular frequency, we simply, again, take 2 pi f. We know the frequency is 3, so 2 times pi times 3 gives us 18.8 radians. So that's the angular frequency. So far we figured out the frequency up here and the angular frequency. Now let's figure out the spring constant. So if we combine this equation with this equation, we'll get that the spring constant is the angular frequency squared times the mass, or 18.8 radians per second squared times 1, and that gives us 353 newtons per meter. Okay, now let's make a slight change here. Let's say, so it says now let's use the same spring and pull it the same amplitude, 2 meters, but let's not start timing until we release it from the amplitude. So notice that the period, mass, and amplitude are all the same. Therefore, the frequency, angular frequency, and spring constant should all be the same too. So all these things are the same. So this is our new graph. It's shifted over some. So if you go back and look at this graph, okay, the position, the difference here is the position starts off at positive 2 meters at 0, whereas here it's not quite at its maximum at 0 meters. So but notice that just about everything else is the same. The period is still the same, okay, and the amplitude is the same. It's actually just kind of easier to read. All right. Okay. So there's some questions it's asking us to find the position when t is equal to 0.10 seconds. So we plug that into this equation from our equation sheet. We know the amplitude is 2 meters. Okay, we get that from up here. 2 pi, the frequency is 3 hertz, and it's saying at 0.1 seconds. So from that, we figure out that the displacement after 0.1 seconds is negative 0.618 meters. So it's somewhere, so after 0.1 seconds, it's somewhere down right around here. Okay. Okay. What is the acceleration when the time is equal to 0.10 seconds? So what we're going to have to do is we're going to have to combine that equation for the force of a spring and Newton's second law to get that equation. We solve that equation for acceleration. We can plug in, we get this equation. We plug in the spring constant, the displacement, which we got from right here, and the mass, get 218 meters per second squared at 0.1 seconds. We're also expected to be able to find the force. So there's 2 ways of finding the force. We can use kx, where we know k and we know x at 0.1 seconds, or ma, where we know m and the acceleration of 0.1 seconds. Notice they're virtually the same value. It's probably off because of some significant figure error. Then to figure out the elastic potential energy at 0.10 seconds, we would use the elastic potential energy equation, 1/2 kx squared. K is going to be a constant. The spring constant isn't going to change. It's going to still be 353. But we know at 0.1 seconds that the displacement is 0.618. So we square that to get 67.4 joules at 0.10 seconds. The total energy we can get from the same equation, but we're going to pull it at maximum distance, at the amplitude. We know the amplitude is 2 meters. So if I plug that in here, the total energy should be equal to 706 joules. So from that, we should be able to find the kinetic energy when t is equal, let's just say 0.10 seconds. Okay, and the way we go about doing that is we use the energy model. If the total energy is 706 joules, and I use 67.4 joules of it as spring elastic energy, The difference is my kinetic energy, or the 638.6 joules. So we're using the energy model to solve for that. Now that we've got the kinetic energy as being 638.6 joules, we can plug into the kinetic energy equation, rewrite this equation for velocity to find that the velocity is 35 meters per second. Okay. And then finally, we can find the linear momentum when the time is equal to 0.10 seconds by plugging into the linear momentum equation. And we'd find that since the mass is 1 and the velocity is 35 meters per second, or approximately 35 meters per second, our momentum is 35 kilogram meters per second. And that's it.